Welcome to Elevate Learn. Today, we're diving into one of the most important concepts in Java programming, object-oriented programming. Whether you're building a simple application or a large-scale enterprise system, OOP principles form the foundation of clean, maintainable code. In this tutorial, we'll explore classes, objects, and inheritance, the core building blocks of OOP. By the end of this video, you'll understand how to design and implement robust Java applications using proper object-oriented design. Let's get started. Here's what we'll cover in today's lesson. First, we'll understand what classes and objects are. Think of a class as a blueprint like architectural plans for a house, and an object as the actual house built from those plans. Next, we'll explore constructors, which are special methods that initialize your objects. We'll then dive into encapsulation, a fundamental principle that protects your data from unwanted access. Then comes inheritance, one of the most powerful features of OOP, which allows you to reuse code and create class hierarchies. We'll see how method overriding lets you customize behavior in subclasses, and we'll use the super keyword to interact with parent classes. Finally, we'll build a complete real-world example and discuss common mistakes to avoid. Let's start with the fundamentals. A class is essentially a template or blueprint. Imagine you're designing a car. The blueprint defines what attributes the car will have, like color, model, and speed, and what behaviors it can perform, like accelerate and brake. An object is a specific instance of that class. So if the class is car, then my red Toyota Camry is an object. Every object created from the same class shares the same methods but can have different attribute values. In Java, we use the new keyword to instantiate objects from classes. We also use access modifiers to control who can access our class members. Public members are accessible everywhere, private members only within the class, protected members in the same package and subclasses, and default members only in the same package. Understanding this distinction is crucial for writing secure, maintainable code. Now, let's talk about constructors. A constructor is a special method that runs when you create an object. It's your opportunity to initialize the object state. The key rule is that a constructor must have the same name as the class and cannot have a return type. Java allows constructor overloading, meaning you can have multiple constructors with different parameter lists. This keyword is incredibly useful here. It refers to the current object instance. If you don't explicitly define a constructor, Java provides a default no-argument constructor automatically. But once you define your own constructors, that default one goes away. You can use the this call to invoke another constructor within the same class, reducing code duplication. This is called constructor chaining and is a best practice for keeping your code dry. Inheritance is one of the three pillars of OOP, and it's incredibly powerful. Instead of rewriting code, you can create a parent class with common functionality and have child classes inherit from it. For example, you might have a general animal class and then dog and cat classes that extend it. In Java, we use the extends keyword to establish this relationship. The parent class is called the superclass, and the child class is the subclass. Method overriding lets subclasses customize inherited methods. For instance, both dog and cat inherit a make sound method from animal, but they override it to return different sounds. Always use the @override annotation. It helps catch mistakes at compile time. The super keyword is your gateway to the parent class. You can use it to call parent methods like super.makeSound or invoke parent constructors. This establishes a powerful hierarchy that keeps your code organized and dry. Encapsulation is the practice of bundling data and methods together while hiding the internal details from the outside world. Think of it like a car engine. You don't need to understand how the engine works to drive the car. You just press the accelerator. In Java, we achieve encapsulation using access modifiers. The golden rule is to make your attributes private and provide public getter and setter methods to access them. This gives you control over what data people can access and how. For instance, you might have a private age attribute with a setter that validates the age is between 0 and 150 before allowing it to be set. Without getters and setters, someone could set age to -5, which doesn't make sense. Protected members are useful when you're working with inheritance. Subclasses can access them, but outside classes cannot. This creates a nice security boundary that protects your code from misuse while still allowing flexibility. Now let's write our first class. Here we have a person class with two private attributes. Name and age. We define a constructor that takes these values as parameters and uses this to assign them to our instance variables. Notice this keyword, it specifically refers to the current object, distinguishing instance variables from constructor parameters. We've provided getter methods to access the private attributes safely. Then we have an introduce method that prints out information about the person. In the main class, we create a new person object called P1, passing Alice and 28 to the constructor. The constructor runs immediately, initializing the object state. Finally, we call the introduce method on P1. This demonstrates the complete lifecycle, defining a class, creating an instance, and using its methods. Pay special attention to how we use private attributes with public getters. This is encapsulation in action. Here's what our program outputs. We see the introduction message from the person object. This simple output demonstrates several important concepts. First, the constructor successfully initialized our object. P1 now has a name and age. Second, the introduce method can access those private attributes because it's a method within the person class. This is encapsulation working perfectly. If we tried to access P1.name directly from outside the class, we'd get a compilation error because it's private. The output string is constructed by concatenating the person's name and age. This is a fundamental pattern you'll use constantly. Define attributes privately, provide public methods to interact with them, and ensure your methods maintain the object's integrity. Notice how the code is readable and the output is meaningful because we designed our class thoughtfully. This is a classic inheritance example. We have an animal parent class that defines common functionality. Every animal has a name and can make a sound. The animal class uses protected for the name attribute because subclasses need to access it. Then we create dog and cat subclasses using the extends keyword. Both inherit from animal automatically. In their constructors, they call super name to invoke the parent constructor. This is crucial. It ensures the parent class is properly initialized. Notice the @override annotation on the makeSound method. This tells Java and other developers that we're intentionally overriding a parent method. The compiler checks that the parent actually has this method. If not, you get an error. Each subclass provides its own implementation. Dog barks and cat meows, but they both inherit the structure from animal. In the main class, we create both a dog and a cat and call makeSound on each. Watch what happens. Even though they call the same method, they produce different output because each class has its own implementation. Look at this output. We created a dog named Rex and a cat named Whiskers. When we call makeSound on Rex, it barks. When we call the same method on Whiskers, it meows. This is polymorphism, same method name, different behaviors based on the actual object type. Neither dog nor cat explicitly defined a name attribute. They both inherited it from animal. The super calls in their constructors ensured the animal constructor ran, setting up that name properly. This demonstrates the power of inheritance. We didn't repeat the name attribute in dog and cat. We defined it once in animal and reused it in both subclasses. If we later decided all animals need a species attribute, we just add it to animal, and instantly both dog and cat would have access to it. This is code reuse at its finest and is a major reason OP is so powerful. Now let's look at a more advanced example. We have a vehicle parent class with brand and speed. Then we create car and truck subclasses that each add their own specific attributes. Car has number doors, and truck has cargo capacity. The key here is how we use super in the overridden displayInfo method. Each subclass calls super.displayInfo first, which prints the common vehicle information, then adds its own specialized information. This avoids code duplication while extending functionality. Notice the constructors too. Both car and truck call super to properly initialize the parent vehicle. This creates a clear hierarchy. Each level builds on the previous one. When we create a car and a truck and call displayInfo on each, we see both the inherited information and the subclass-specific information. This is a powerful pattern for building extensible code. Observe the output carefully. For the Toyota car, we see the brand and speed from the parent vehicle class, followed by the door count from the car subclass. For the Volvo truck, we see the same parent information, but then the cargo capacity from the truck subclass. This layered output is exactly what we programmed. By calling super.displayInfo in each subclass's overridden method, we reused the parent's formatting for brand and speed, then added our own information. This is much better than copying the parent's code into each subclass. If we later changed how vehicle displays its information, the change would automatically apply to car and truck. Each subclass properly initialized all attributes through constructor chaining with super, ensuring no data is left uninitialized. This demonstrates professional OP design. Let's apply what we've learned to a real-world scenario. Every company has employees, but different roles have different responsibilities. We create an employee-based class with common attributes like name and salary. Both managers and developers are employees, but they have different bonus structures. A manager might get a bonus based on salary plus team size, while a developer gets a straightforward percentage. We create manager and developer subclasses, each with their own attributes and overridden calculate bonus method. When we call display role on a manager, it shows their team size and calculates their bonus including the team incentive. For a developer, it shows their programming language and calculates their straightforward bonus. This shows how inheritance supports real business logic. If the company wanted to add a designer role, we'd just create a new designer class extending employee with its own bonus calculation. The structure scales beautifully without modifying existing code. Let me highlight some critical patterns and anti-patterns. First, never duplicate code across similar classes. If dog and cat both need a name and age, that's a sign they should inherit from animal. Second, never make attributes public just to save typing. Private attributes with public getters and setters give you control and protection. If you later decide to validate age when setting it, you can do that in the setter without breaking code that uses your class. Third, always use super in subclass constructors to properly initialize the parent. If a parent attribute isn't initialized, your object is in an inconsistent state. Similarly, use super.method when overriding lets you extend behavior rather than replace it entirely. These patterns make your code maintainable, flexible, and less error-prone. They might seem verbose at first, but they're investments that pay off immediately in code quality and long-term maintenance. Quick knowledge check. What's the difference between a class and an object? Think about the difference between architectural blueprints and an actual building. A class is like those blueprints. It defines what properties the building will have and what it can do. An object is the actual building constructed from those blueprints. In Java, a class defines structure and behavior. An object is a specific instance created from that class. Here's another important concept. Why make attributes private? If age is public, someone could write myperson.age equals -5, which is nonsensical. A private attribute with a public setter can validate. setAge checks that age is between 0 and 150. Another benefit. If you later decide to store age as a birth date instead of an integer, you can change the internal implementation. Code using your class still calls getAge and setAge, and everything works. With public attributes, changing your internal representation would break everyone's code. Private attributes also prevent accidental misuse. Instead of directly accessing myperson.salary, the proper way is through getSalary. This creates boundaries that protect your code. It might seem like extra work writing getters and setters, but it's an investment in maintainability and robustness. Let's discuss the super keyword. In inheritance, super is your connection to the parent class. When you write super in a subclass constructor, you're calling the parent constructor. This is crucial because it ensures the parent's attributes are properly initialized. For example, if animal has a constructor that sets up the name and dog extends animal, the dog constructor should call super name to set up that inherited name. Without super, the parent's initialization is skipped and your object is in a broken state. Super.method lets you call the parent's implementation. If dog overrides make sound, but wants to also do what animals make sound does, you can call super.makeSound. This is how you extend behavior rather than replace it entirely. The super keyword is essential for writing correct, maintainable inheritance hierarchies. It's one of the most important tools in OP programming. Congratulations! You've mastered the fundamentals of Java OP. Let's recap what we've learned. Classes are blueprints that define structure and behavior, while objects are specific instances of those classes. Constructors are your opportunity to initialize objects properly, ensuring all attributes are set up correctly. Encapsulation is about protecting your data. Make attributes private and provide public methods to control access. Inheritance lets you create hierarchies where subclasses reuse and extend parent code. Use the @override annotation to mark intentional method overrides, and leverage the super keyword to call parent constructors and methods. Access modifiers control who can see what, use them wisely to create secure boundaries. Finally, always write dry code. Don't duplicate logic. These principles make your code maintainable and professional. As you continue your Java journey, remember that good OP design is about balancing protection, reusability, and clarity. Practice these patterns, and you'll write code that scales beautifully and stands the test of time. Thank you for learning with Elevate Learn.